All right, so now we are going to actually move further along with Monte Carlo simulation. Last week we did spend a lot of time looking at the statistical background going on behind the scenes with Monte Carlo simulation. Now we want to take all of this information and apply it to a specific example, which means option pricing theory. Specifically, what we're going to do is take all that statistical information we used last time and take the um, Black-Scholes model and use it for simulation first of European options, and then we'll extend it to more complicated situations. But first, we want to always start by using the simplest possible case. And of course, with Black-Scholes, we have something to compare our results to, so we can get a sense of how many paths it might take to get our answer very close to the Black-Scholes price. And once we're satisfied with our results, then we can go ahead and try other more complicated types of options. So here in the slides, you'll see that we're going to introduce or reintroduce the stochastic differential equation that is used in Black-Scholes. And this is what we call geometric Brownian motion. And by the way, this is Robert Merton's idea. In the original Black-Scholes framework, they were going to base it on the capital asset pricing model, but Merton convinced them to switch to geometric Brownian motion because that way the model could be extended to price options other than equity options. So he went out, and that otherwise we might never have heard of Black-Scholes. So this is a stochastic differential equation. And basically, it's an attempt to model a variable that has a fixed component, a fixed trend that is, and a stochastic or random component. And so you can see here from these terms, ds is the instantaneous change in the asset price, which in the case of Black-Scholes would be the stock price. See, instantaneous change in S. And of course, dt is the instantaneous change in t. Or time. And now the dz is actually the geometric, it's Brownian motion. The entire process is called geometric Brownian motion. It is an extension of the basic Brownian motion process, which is right here. And then we also have R, the risk-free rate of interest. Q is the yield of the underlying asset, if there is one. And if you notice, the way this is written, it's understood that R and Q are both continuously compounded. Okay, this is the asset price at whatever point in time we're looking at, as is this. Oops. And then the sigma is the volatility of the asset, which basically means it is the standard deviation of the continuously compounded returns to the asset. This is how volatility is actually measured. So as I was saying before, the trend term is here. And if you notice, there's no stochastic terms in this because this basically is telling us that the price will increase at this rate, and the actual, or I should say, the percentage change is R minus Q, but when we multiply that by S, we get the actual dollar change. And then this tells me the interval over which this happens. So you can imagine if you just plotted this, it would just be a straight line. Okay, it means that as time evolves, the whatever this asset is, its price is evolving linearly as a function of R minus Q SDT. The stochastic component or random component is this sigma S dz. The dz itself is a random variable. So let me just, running out of space. I'll have to move this to a new document. So I think I used this analogy once before. Brownian motion is like essentially a continuous time version of the random walk process. So if this is our random walk, now the random walk basically just means that wherever it starts from, it just randomly goes up and then down and then up, down, up, down, up, down. But in such a way that on average it should return to its origin. So there's the expected change in this process is zero. Okay. Sure, it can go up and down, but on average, it should come back to this long run average. So it's like imagine that you're in a situation where you're flipping a coin, and whenever the heads comes up, you win $1. But if tails comes up, you lose $1. So in a game like that, if you start out with $10, you'd expect that in the long run, keep playing this game, you'll end up with $10. Okay. Um, but here's the interesting twist. As time elapses, you can get further and further away from the $10. So you could get into lucky winning streaks, you could get in unlucky losing streaks. So the process can get further and further away from that $10. So what this is telling us is that the expected value of DZ is simply zero. The variance is the change in time, meaning step from here to here, for example. And then the standard deviation would simply be the square root of that. Okay. That's the basic Brownian motion process. All right. By itself, Brownian motion is simply a random variable that, oh, and one more thing I almost forgot to mention, DZ is normal. That's a pretty important detail. Yes, DZ is normal. With those two properties, on average, it should be equal to zero, or the changes in the process should be zero. But the volatility increases linearly with the square root of time. So that's why you see it can drift further and further away from the $10 that we started out with. Okay, so then when you add other terms to the geometric Brownian motion, sorry, hold on. Now that by itself is fine as far as it goes, but it doesn't help us explain most assets we observe in the marketplace. Yeah, I have to clean this up just a little bit. Wow, I really made a mess out of this. All right, I'll tell you what, let me just draw this again. I'll put these over here, I guess. Okay, I think we're in good shape now. So I'll draw the picture one more time, but all you really need to notice here is that wherever we start, and it could be zero, by the way. If you start at zero, but if you start at zero, then the process can have positive and negative values. You can have something like this. At first, it stays very close to the zero, but then as time goes by, it can get pretty far away, but on average, it should end up back at zero. Now, this is the random walk process. You notice it's discrete. The reason why it's jagged is because each of these changes takes place over a finite interval of time, which is delta t. So it is a discrete process, meaning that it's happening at specific time intervals. Like, let's say we're flipping the coin, and it's only possible to flip the coin once a second. That means dt, delta t, is a second, basically. And so we flip the coin, we observe the outcome, our winnings or losses change. And so it goes up and down. So you can imagine this up and down business is the value of our winnings or losses. So here, for example, we've won several dollars. Here we've lost a little bit. But again, on average, if you just keep playing and playing and playing, you would expect to go home exactly breaking even. If we change the delta t, um, or we let it go to and converge to zero, we eventually end up with a smooth continuous process, which behaves in the same way, except that in the limit, these moments are going to be a little bit different. Sorry, it's regular geometric, regular Brownian motion, just Brownian motion by itself. Um, Maybe I can try to draw that a little bit better. I really like it to look very much like the random walk, although I mean it doesn't have to, as long as it has the same properties. Again, I really want to make sure that it's clear that well, we can drift further and further away from the origin here. On average, we should always wind up back at zero. So once we have this process is taking place an infinite number of times, it is said to be continuous. And the moments are going to change slightly. Suddenly we're looking at not delta t, but dt to indicate that this is a differential rather than a small change, which delta represents. Now, what about geometric Brownian motion? Well, geometric Brownian motion, oh, and by the way, in case it wasn't clear, this one is also normal. And this is part, the foundation for what Black-Scholes is built on. So for a more complicated situation, we can adjust this model. And so the so-called geometric Brownian motion process looks like this. Basically, it uses the Brownian motion to account for the randomness of the process, But then we also assume, because this is a financial asset of some kind, that over time, its value will grow at a predictable rate on average. Okay, so that's where this is coming from. So they're claiming now, in keep in mind too, remember, we're assuming that we're in a risk neutral world here. So the growth rate of this asset should be based on the risk-free rate of interest minus any cash flows that are being paid. So what the geometric Brownian motion is doing differently is that it has that drift, which we don't have with regular Brownian motion. And also it makes it possible to have some kind of, let's say, trend that you wouldn't get with the geometric Brownian motion. So in other words, instead of having this kind of thing, sort of this aimless wandering up and down around the origin, instead, you'll see that there's a positive amount of growth taking place. So you can have to visualize that this is more what we're seeing. So in other words, it's the variable, whatever it is growing over time, but we still have this random bouncing around that trend line. And I think it's pretty clear that this is a much better description of how, let's say, a stock price would behave than the Brownian motion, where on average you're breaking even. Nobody would buy stocks if you're breaking even on average. So this is what is being assumed by Black-Scholes. So underlying all this is the assumption that the rate of return to this asset, whatever it is, okay. So yes, that's one of the fundamental assumptions of the Black-Scholes model. And this is why, by the way, because they're assuming that stock prices follow geometric Brownian motion. Okay. So anyway, so what we're going to do with Monte Carlo is we're going to say, listen, let us take this geometric Brownian motion process. Now we have to break it down into discrete steps. I mean, the Brownian motion generates paths, but they're not actually continuous. We can have very small time steps, but we're still going to have something like this, where we have discrete time steps, and the asset is allowed to move around according to the geometric Brownian motion process. But the Monte Carlo simulation comes from the fact that we're actually simulating the Brownian motion part. That's where the simulation comes in. The rest of these terms are just constants. This is where the simulation actually takes place. So all the details that we looked at last week, choosing from the uniform distribution, plugging them into the inverse normal distribution, that's being done to simulate DZ. And then the rest is, like I said, are just constants, and that will give us the increments to our asset price. Anyway, so let's go back to the code and see what that's all about. But first, let's go through the slides. Oh, by the way, I do want to mention here that for any asset that we're pricing with Monte Carlo, at least here, presumably stock prices, the Black-Scholes model assumes that returns are normal. That implies that the prices themselves are what's called log norm. Oh, and by the way, these returns are assumed to be continuously compounded. So the prices would look more like this. Okay, the log normal distribution is skewed to the right. It doesn't have any negative values. So luckily, this geometric Brownian motion model does preserve these properties. But here's the interesting part. This, when turned into a discrete time model, turns into this. Okay, so for the most part, this is very straightforward. The differentials are replaced by deltas. The only part that's a little bit, like you're probably wondering about is this part. What you're seeing here is actually epsilon is a standard normal random variable. And when you multiply that by the square root of delta t, which is a constant, it has the right moments. In other words, I'll move these up here. The expected value of this term is 0. And the variance is delta t, and the standard deviation is the square root. And of course, since epsilon is normal, multiplying this by a constant doesn't change that. So you can think of this epsilon square root of delta t as the discrete time version of Brownian motion. Now, this is really what we've been building up to because epsilon is a standard normal random variable. We saw last time how to simulate that in a two-stage process by simulating from the uniform distribution and then plugging it into the inverse normal distribution. In fact, let me just see if we can go back and quickly revisit. We had that one document with all my handwritten notes, which shows the graphs that we need. There it is. Yes, so we remember we went through all this last time, all this statistical discussion, but ultimately what we're aiming for is to be able to show why it's possible to simulate from the standard normal distribution by choosing a random number from the standard uniform and plugging it into the so-called inverse of the standard normal distribution. So like here, for example, if we randomly simulated 0.8413 from the standard uniform distribution, that maps to 1 under the normal curve, and therefore 0.8413 is replaced by 1, which is a normally distributed value. Okay, or chosen from the normal distribution. So this is how we're going to find the values of this epsilon term for our model. Okay, so there's all of this work is being done to simulate epsilon. So once we have an epsilon, which has to be standard normal, we can plug it in here with all these other constants, and we'll be able to determine what is the new value of the stock price. All right, well, you'll see when we get to the code, but this is where the simulation is actually happening. So we're not simulating directly from the standard normal, we're simulating from the standard uniform because this is a more general approach. I can later on change this to a different distribution. I could simulate from the t distribution, for example, as long as I have the inverse function for the t distribution. All right, so Now, like this has happened before. We sometimes it makes sense to simulate not the variable itself, but the log of that variable. If we do that, um, then you're going to change the stochastic differential equation a little bit. And then at the end, you have to convert it back to the original level. But sometimes it speeds things up a bit. And remember, with Monte Carlo simulation, speed is of the essence because it's such a horribly time-consuming process. So if you do that, um, it turns out that you can actually simulate with this expression. So you notice how this is the part that's being simulated. And then you've got all these other constants. And if you notice, this is a recursive process because now the stock price depends on what happened the day before. So we simulate, we're basically doing the same. Where's the stock now? We simulate epsilon, plug in all these constants, and that will tell us where to go the next day. Because ST minus 1 is in fact delta S. Okay, so it's written this way so that we can just plug numbers in and then find out what the next value of the stock is on our path. All right, so now here I have a very simple example, just to show how this works. Suppose we have a stock whose volatility is 20% per year. The volatilities are always quoted on a per annual basis. The risk-free rate is 5. Again, that's always quoted on an annual basis. And what else do we know? Q is 0. There's no dividend or any other cash flow. And then the time step, we're going to do this every day. Okay. So that means, and by the way, with these types of models, we only are interested in trading days. The theory is that if this is a stock, it's not going to trade on the weekends, or at least not very much. There might be some overseas markets that are open, but for all practical purposes, the bulk of the trading takes place during the week. So in principle, the volatility should be 0 over the weekends and any holidays. So we're going to assume, which is a fairly standard practice, that we only have 252 trading days in a year. So delta T will be 1 over 252, which is simply 1 trading day. So that's where that's coming from. Now, if you plug those numbers in here, although I kind of skipped over some steps here, you'll see that all the constants end up looking like this. And you see the only part that still needs to be simulated is right here. So what I did here was and in the slides, you'll see how this worked out. For the next 10 trading days, pick a random number each day from the standard normal distribution, plug it into epsilon. So here you can see the results. Days time 0 to 10. And each day, this is a standard normal random variable. And so what happened, is that if you then, and you can see this is clearly done in Excel, if you plug this epsilon into this equation, in fact, why don't we confirm it right now? The initial stock price is 100. So the epsilon, that is, turned out to be 0.4403. And so I'm going to plug this into the calculator right now, just out of curiosity. There's probably some rounding involved. Here we go. I'm dying to see this now. So it should be $100.57. Yeah, there it is. Okay. And so what it's saying here is that if S0 is 100, the first epsilon that we choose, we'll call it epsilon 0. Actually, no, I think we're going to call that epsilon 1. Let me just check. Yeah, let's call that epsilon 1. Implies that S1 is 100.57. So now we choose another epsilon and plug that in here to this model, except now we're going to look for S2, this and S1, and then all of this and the new epsilon. Okay, and so that happens every day during this path until we get to the end on day 10. So this is the path that we created. The 100 is the only observable value. The rest are simulated. And if you drew a graph of this path, it looks like this. Okay, so it's a simulated path. And so if we want to price an option, what we would have to do is, let's say it's a European call. This is the date on which the option matures. And so if, for example, the strike is 102, this is my payoff. The value of the option today would be the present value of that payoff. Now, of course, the chances of this being the right price are pretty remote. So what would happen is you do another path and another and another. Each time you calculate the price of the option. Like there, yeah, you can see even after 10, look at what happens. So you've got what you're actually creating is a probability distribution for the stock price, which in turn generates a probability distribution for the option price. The center of that distribution is our simulated option price. Okay, so I don't think I have a graph like that here, but what you can do if you wanted to in Excel, you could just run through and simulate a bunch of stock prices and then calculate the corresponding option prices and then graph them side by side to see what you end up with. We know that the paths, stock prices are log normal, but the options prices are not necessarily going to follow any particular distribution. But whatever we end up with, say we have stocks here, and then let's say I don't know, it could be a lot of things. Let's say this is the option distribution. The center here, that would be our simulated option price, the center of that distribution. Okay, so this is what we're going to accomplish. So I'll tell you what. Well, actually, this is another example. We have a European put, and then we'll get back to the code. Okay, European put written on the stock matures in 10 days, and it has a strike price of 101. Now, if you notice, what this is saying is that the put price is the average payoff of these paths discounted back to the present. We always have to discount it back because the payoff occurs in the future. Okay. That's why this is here. But the E part, the expected, is that this is basically the average payoff on all the paths that we create. So it's really a simple process in that way. Average out the payoffs on those paths, and then whatever that average is, we discount that number back to the present, and that gives us our option price. So I went ahead and did, and the thing is, when you look at these, 10 paths is nothing. I mean, the chances of getting an accurate price are very low. How do you know, by the way, how accurate your numbers are? Well, what we typically will do is calculate the standard deviation of the simulated prices. And then we'll calculate the standard error because this is a sampling distribution. And so this is the number that we want to see as small as possible. Now, by the way, this gives us some insights into why the Monte Carlo system, Monte Carlo is so time consuming. If you notice, the standard error is reduced proportionately to the square root of the number of paths. So in other words, if I want to reduce the standard error, I want to cut it in half, I have to have 4 times as many paths. So that shows you like why this can take so long, because the standard error, it shrinks very slowly. Let's put it that way. Okay, now see, now the other thing about the standard error, which is great, is it because we can create a confidence interval based on our results. Okay, and that confidence interval will give you a sense of how close we are likely to be to the true price of this option. Now, this one with 10 paths, you can see the standard error is about 82 cents. So look at this confidence interval. We're 95% sure, based on these results, that the price of this put is between 90.5 cents and $4.18.1. Now, that doesn't give me a whole lot of confidence in my results. A trader would never accept this. So the only way to get around this problem is to greatly increase the number of paths. And so, God, imagine if you needed to be within a penny of the actual price, how many paths you would need. I'm sure we could solve for that. If S is 259, we need S over radical N to be a penny, let's say. So that many paths would reduce the standard error to a penny. Let's see what that is. Oh, that's interesting. It's only about 67,000 paths, but that's still a lot of paths. Okay. For some cases, it can be in the millions. All right. Well, anyway, and yes, I went ahead and calculated the Black-Scholes price. It's 280. I'm sorry, 180. We ended up with an estimate of 2.538. So we're off by 70 something cents. Seems like a lot. So what I did here was I also increased the number of trials or paths. And eventually, I mean, if you keep doing it enough, eventually you'll get very close. Now, the next discussion here is it's a brief discussion of techniques we can use to reduce the number of paths that we need. But before we do that, let's go look at our code for a second and get a sense of how all of this is being implemented. Because I know we haven't had an assignment yet. I would like the first assignment to be based on Monte Carlo. So why don't we look at how we would price a European call option, and you'll see it's surprisingly straightforward. Um, so let's get that open. Actually, I think we had this open last time when we were looking at the button. Um, you can see now the way this is set up, there's only 10 paths. So when you run it, look how much it changes from one time to the next. It's pretty scary how much, and also the standard error here is $1.23, which is absolutely astronomical. So if you were to, let's say, increase this to 1,000, the standard error will reduce to, oh, wait a minute, sorry. You know what I just realized? I think I misunderstood my own notation. It's the capital N is the number of time steps per path. It's capital M that represents the number of paths. Yeah, that's more like it. So you can see M, the number of paths, I just increase it from 100 to 1,000. If I increase it to 5,000, the standard error is down to 18 cents. So you can see. Now, by the way, you have to be careful here. Don't overdo it. If you accidentally ask it for some astronomical number of paths, your Excel could be locked up for a long time. I mean, I think there's a way to stop it, but just be careful. You can see we're down to 12 cents. We could try 20,000, for example. You see, it hesitated about 9 cents. So if we keep doing this, we'll get closer and closer. And you notice how now each time I run it, it's not that far from the previous ones. We're looking at a spread of 10 or 20 cents, whereas before it was just all over the place. But if you look at the code, here we go. Now, of course, there's always a ton of documentation. But what I'd like to do is let's take a look at the basic logic. You know what I'll tell you? Let me copy this onto a Word document so we can read it better. So notice here, um, these are the constants of the problem. And actually, so is this because that's the log of 100. That's the natural log of 100. So in this code, we're actually going to use the logarithmic approach. All right, let me this in here somewhere. Oh, we don't need. Okay, so what model are we following here? Remember earlier we said that we could use logs if we chose to do so. So yeah, we're using this approach. And um, that implies, I'll write this down. So I'm not sure if I can copy this. Nah, it looks like a mess. I was afraid of that. All right, let's try this. So that indicates because this is delta log, rewrite it like this. Now, in this code, you'll notice that there's some abbreviations here. All of this is being replaced with this term. This is actually the Greek letter nu. It's being used to represent the so-called drift term of this process. So in the code right there, NUDT, it refers to this. And then this other one, just this part by itself, in the code appears as SIGS DT. And the reason why it's done that way is so that that can be multiplied by our epsilon. Also, if you notice, we had to tell VBA that we're taking the natural log. This is one of those cases where there's a different function in VBA and in Excel. So in VBA, the natural log of x is expressed as log. In Excel, it's ln. Okay, so but whenever we have a conflict like that, we always use the VBA version. So this is telling the code is saying take the s, whatever it is, and take its natural log. And these are two constants that we'll need. So when we're done, it can be reduced to a very simple expression. Here's dt. We've seen this before. That's the size of a single time step. All right. So oh boy, I'm trying to line it up properly. There we go. So anyway, so this way you'll see what this code is all about. Now, what comes next in the code? Yes, and this is where before it's in the documentation, but we're using n, capital N, to represent how many time steps are there in each path. So in other words, let's say this is a 10-day, it's 10 days to the maturity of this option. All right, I got one too many in there, but that's what we're trying to show. This would be our capital N. And then M, capital M, would be the number of paths. So if we repeat this process 5 times, let's say 5 paths, each of which contains 10 time steps. Okay. So that's what that is in the code. Now, you'd be surprised. By the way, this is all housekeeping up here. You know, there's the only thing. Oh, by the way, here's an interesting side note. Since we're using random numbers, there's a command in VBA called randomize. And what this does is make sure that every time you ask for a string of random numbers, that they'll be different. Because if you leave that out, you could actually end up with the same random numbers every single time. So randomize just makes sure that it's not always giving you the same ones. These are the constants. This is where it prints out the constants. Now these are counters. These are used to help us calculate the standard deviation of the prices we get on these paths. This is so that we can calculate the standard error and construct a confidence interval. And so anyway, the basic loop is here. So the index runs through 1 to m. This will do this, what we're about to see for each path. Within each path, we start by taking the logarithm of the current stock price as our starting point. Then I equals 1 to n keeps track of the time steps on a single path. Now, here's the part that we spent so much time with last time. Epsilon is application dot norms in rand. Now, again, the spelling is consistent with VBA. In Excel, this is spelled rand, R-A-N-D. But in VBA, it is R&D. So what they're saying here is choose a random number from the standard uniform distribution and plug it into the inverse standard normal. That will give you a single normal random number. That we'll call epsilon. And now, if you look at this statement here, what it's saying is whatever your current log price is, add to that new dt, which, as we know, is this drift term, plus, and then you notice how this is sigs dt. We're going to need to multiply that by times epsilon. So that way we've got both parts of what you see in the brackets. All right, so the current price, the current log price, to that add new dt plus sigs dt times epsilon. And that brings us to the next step on our path. Go through, and you see the next here. That means this loop is ending. So in other words, within each path, we go through all the individual time steps. When we get to the end, we're going to store. Oh, well, actually, at the end, we've got a log of our stock price. We have to turn that back into a regular price by taking e raised to that power. And then we have to figure out the payoff. Now, this is a call, so the payoff is the stock price minus k over 0. And then this part, like I said, is just calculations for the standard deviation. Then this next refers to the paths. So we go to the next path and do the same thing, and again, and again, and again. And when we're done, we figure out the standard deviation, we figure out the standard error, we construct a confidence interval, and print out the results. Wow. Okay, so let's go back to the front page of the spreadsheet. You can see here, we've got all the information, the upper and lower limit. This is the center. This is the predicted or expected option price based on our Monte Carlo simulation. So here we get to choose the number of time steps per path, as well as the number of paths. Okay. Now, the same thing is true for the put. The only change, as you can probably guess, is right. Where is it? Wherever the payoff is, that's where the change is. There's a single change, and that would be for the payoff. Here it is. That's literally the only change you would have to make to turn it into a put. And so there is a separate program for that, but so you can run it here, you can see same thing. Now here I've got 1,000 paths, so the standard error is only about 27 cents. So this one isn't bouncing around quite as much as this one was. So those are the basics of pricing a European option with Monte Carlo. So what we would like to be able to do is, maybe go through this one more time and really understand it, but also to try our hand at pricing more complex options. And it can get a little messy, but the basic simulation part doesn't change. It's just a question of keeping track of information about the path so that we can price the more bizarre options that are out there. So here, we didn't need to do that. You notice we didn't store the individual values along the path, but with path-dependent options, we do need to keep track of all the every single time step. That way, for example, we can tell if a barrier has been reached or something like that. Okay, so that will be very interesting. I think you'll agree, but I guess for now we can stop it right here. And then the next time we'll try our hand at an exotic option just to see how that goes. And then when that's over, we're ready for finite difference methods, which will remind you a lot of what we were doing earlier. And then these are a more detailed discussion about interest rate derivatives and the term structure of interest rates and how they're modeled using these techniques. So, all right, anyway, so we'll stop here and I'll see you next time.